Welcome to section 3.7, implicit differentiation. The difference between an explicit function versus an implicit one is that in an explicit function, this is where we clearly have a function expressed in terms of only one variable. Normally, we write it f of x or f of whatever variable we're using, or just y equals. Note that on the right side of the equation, our function is only defined in terms of x, no other variables. These are the types of functions we're most used to, and these are the types of functions that we so far have learned how to differentiate with specific rules. An implicit function is one that is implied, but this is a case where we don't just have a simple y equals or f of x equals. It's actually difficult to express y in terms of x here because of how the variables are kind of together. We might even have some that have like xy in the same term. So we may or may not be able to separate the variables. It's not always that we can't, but it's very difficult to get y equals. And so in an implicit function, we're actually defined kind of by two variables, in most cases x and y. Let's look at a very simple function down here. And let's say we have the function y equals 1 over x, or x to the negative first. This function is defined explicitly, y in terms of x. However, if we multiplied both sides by x, we would have xy equals 1. This is the same function as this, except in this case we're defined explicitly, and in this case we're defined implicitly. Some functions we can do that with if they're simple, like this one. However, in this case here, it would be very difficult to express this in terms of y. So today we are going to be learning how to differentiate or find the derivative of implicitly defined functions or implicit functions using a process called implicit differentiation. Our first example is fairly simple. We have the implicitly defined function which could be explicitly defined, y cubed equals x. And so I picked this to start with because it is fairly simple. So what we are going to do is we want to find dy dx, or the derivative of y with respect to x. So every time we take the derivative of a variable that is not x, we have to put dy dx by it since it's y. Let's take a look at this. I'm going to write it out in good calculus notation here. So we're taking the derivative of both sides of the equation of every single term, and we're taking the derivative with respect to x. All right, the derivative of y cubed with respect to x is going to be 3y squared using the power rule. But then since the inside function y is not x, and we have to take the derivative with respect to x, we need to use the chain rule and multiply by the derivative of y with respect to x. That is dy dx. On the right-hand side, we're taking the derivative of x with respect to itself. So the derivative of x is just 1, and technically we could multiply by dx, but that's just 1. See, we don't need to invoke the chain rule here because this matches this. So with implicit differentiation, anytime we have a y and we're taking the derivative of y, since it's not the variable with respect to down here, we have to do a dy dx after it. Now lastly, what we need to do is solve for dy dx, and that involves a couple algebraic steps, and in this case it only involves one. We're going to divide both sides by 3y squared to get dy dx by itself. So we'll have dy dx equals 1 over 3y squared. Now, in this case, we would say that the only time the derivative is undefined is when y is 0, since that would be the only value that, if we plugged it in, would make our denominator 0. This next example is a little bit more complex, and it's a good one. We see that we have an implicitly defined function, a function defined in both terms of x and y, and so what we want to do is find the derivative of each term here, both sides. So we can see that we have a product here. We'll need to use the product rule. 7x is also a product, but we don't need to use the product rule here because both of the factors don't have a variable in them. And then this is just the sine of y, so we'll need to use our rule for how to take the derivative of trig functions like sine. Okay, in our first term here, well, first let's say we're taking the derivative of the whole thing with respect to x. So we're taking the derivative with respect to x of this entire function. So just some nice calculus notation to say we're ready to take the derivative with respect to x. All right, in our first term here, x cubed y, we need to use the product rule. So I will write out what u is. U is going to be x cubed, and v is y. Then u prime is 3x squared. It's with respect to x, so we don't need to use the chain rule. V prime, the derivative of y would be 1, and then dy dx. So I don't need to write the 1, it's just dy dx. Okay, now we can go ahead and use the product rule there. So it's going to be u times v prime, so x cubed times dy dx plus vu prime, so y, and I'm actually just going to write it in this order instead, 3x squared times y. All right, so we've taken the derivative with respect to x of our first term, and we needed to use the product rule. The derivative of 7x with respect to x is just 7, so that next term's pretty simple. So plus 7 equals, now we want to take the derivative of sine of y with respect to x. The derivative of sine of y would be cosine of y times the derivative of y dy dx. So this will be the cosine of y times dy dx. Now our ultimate goal is to isolate dy dx. So from this point, we are done with the calculus. We've found the derivative, but now we need to use algebra in order to get dy dx by itself. Now we note that we have 4 terms here, and out of those 4 terms, 2 of them have dy dx in it. What we need to do is get those 2 terms with dy dx in it to the left-hand side of the equal sign. We need to get the 2 terms that don't have dy dx in it to the right-hand side. Does it matter which side we put it on? No, not really, so long as all your terms with dy dx in it are by themselves on one side. I just personally like to have the thing that I'm solving for on the left. So what I'm going to do is subtract 3x squared y from both sides, subtract 7 from both sides, and subtract this cosine y dy dx from both sides, just rearranging in this next line. So the only thing that's staying is this first term, x cubed dy dx. We'll have a minus cosine y dy dx as well. And on the right-hand side, we'll have a minus 3x squared y and a minus 7, just with that algebraic manipulation there and subtracting. All right, now the reason that we want to get all those terms with dy dx and them on the same side is that we can factor out the dy dx, and that'll get it by itself. When we factor the dy dx out of both of those terms, in this term here we're left with x cubed, and here we're left with a minus cosine y. On this side, we haven't changed anything. Then we can divide by this x cubed minus cosine y from both sides to again isolate the dy dx, which is what we're solving for. So dy dx, our derivative of this implicitly defined function, is defined in both terms of x and y. And there it is. Messy, but our final answer. So we have talked about this process in 2 examples, one more complex than the other, but this is the implicit differentiation process. I wrote this down verbatim from your book, so if you'd like to take a look in the book, you may. It's the same info there. But we differentiated both sides, or every single term, in our equation with respect to x. We got all the terms with dy dx in it on one side, and all the terms without dy dx on the other. We factored out dy dx, and then divided to solve for dy dx. Here's another example of where we need to find dy dx of an implicitly defined function. Then what we're going to do is actually plug in when x is -3 and y is 1 in order to find what the value of dy dx is, our slope, at that point. So what we're going to do is first take the derivative with respect to x of this whole thing. So I'm going to do d dx of this entire thing, meaning both sides. So we want to first take the derivative with respect to x of x squared. Using the power rule, that is simply 2x. On the right-hand side, we see that we have a quotient. So we need to use the quotient rule. And recall that the quotient rule has a fun little saying, low d high minus high d low, all over low squared. So our low is our denominator, which is x plus y, times the derivative of our high, the numerator. The derivative of the numerator is going to be 1 minus dy dx, the derivative of y with respect to x. So 1 minus dy dx minus high, x minus y, our numerator, times the derivative of the denominator, d low, which is 1 plus dy dx, all over low squared. Okay, the next step is to simplify in the numerator. It looks pretty complex, but I have a feeling that a lot of nice things will cancel out here. So we will multiply. I'm first going to distribute the x through to the 1 and the dy dx, then distribute the y through. All right, I did a couple things in that step. I did what I said I would do here by multiplying through. I then multiplied through here and kept it all in parentheses since we are subtracting. So in the next line, what I'm going to do is distribute this minus sign through. Actually, we can do that right here by just distributing the minus sign through by changing the sign of each one of these four terms and then taking the parentheses away. So that's what I'll do here. So I'll do that in dark blue so we know when we've done it. So that turns into a minus. This here will turn into a minus. And here we'll turn to plus and plus. And we can get rid of this minus sign out in front because we just distributed it through, and the parentheses can go away. And then we can see if anything ends up canceling. So it looks like we do have a lot that cancels. We have a positive x and a minus x. We have a minus y dy dx and a plus y dy dx. All right, in our next line, what I'm actually going to do is combine some like terms. So we have a minus x dy dx and another minus x dy dx. So we have two of those. So minus 2x dy dx. Then we have a plus y and another plus y. So we have two of those. And that is still all over x plus y quantity squared. Now, our goal is to get dy dx all by itself, and usually I say get that on the left. In this case, I guess I'll keep it over here. So I'm going to multiply both sides by the denominator to get rid of it. So we'll have 2x times x plus y quantity squared, and when we multiply the right-hand side by that, it cancels with the denominator. Now what I'm going to do is subtract 2y from both sides, and that'll leave the term with dy dx all by itself. And then what we can do is realize that all three of these terms actually have a 2 in them. We'll see that they will end up canceling. If you'd like to cancel them here, you can. But I don't want to get too far ahead of myself. So I'm going to do to both sides to solve for dy dx. Since we don't have to factor it in this case, we only have one term with dy dx in it, so no factoring is necessary. All we need to do is just divide by the negative 2x on both sides. And actually, I'm going to just do that by dividing each term by it instead. So minus 2x minus 2x. All right. You can do this really in any way you'd like. I just kind of want to show what's happening here. So dy dx equals, here we can cancel, and here we can cancel, and it'll turn into a plus. So what we have is a negative x plus y quantity squared, then just plus a y over x. Now, if you did not do all that simplification and just divided this whole side by negative 2x, that's also fine. We are plugging in a number anyway to get our final answer, but we do have that, which is great. All right, that was kind of a crazy problem. So we want to plug in now negative 3 comma 1. So that's our second step here. So we have our implicitly defined derivative. Also, it's implicitly defined because it's in terms of both x and y. So what we want to do is figure out what this slope of our curve equals. What is dy dx when x is when x is negative 3 and when y is 1. You can also write this down here looking like just the coordinate point. So I'm just showing you kind of two ways. I think the book writes it like this instead. Either way is totally fine. It means we're about to plug in. So we want to plug in x as negative 3 and y as 1. So we're going to have negative 3 plus 1, quantity squared, plus 1 over negative 3. We could also write that as minus 1/3. All right, when we keep going here, we'll simplify. So we have negative and then negative 2 quantity squared minus 1/3. That's going to give us 4 and then times that negative out front. So it's negative 4 minus 1/3. So we could simply write this as negative 4 and 1/3. Or we could write this as, I'm doing the math quick in my head, negative 13 thirds. So either one is totally fine. So we know that at that point, our tangent line would be a pretty steep negative line since its slope is a pretty negative number. In this problem, we want to find the equation of the tangent line to this ellipse. Ellipses are like ovals, if you remember back from pre-calc, at the point negative 1, 2. So the first thing that we need to do, again, in order to find the equation of any line, you need a point. Cool, found it. Oh, there it is. And the slope. So dy dx at when x is negative 1 and when y is 2. So that's the hard part. That's the calculus part. So what we're going to do is we are going to find d dx of this function right here. We're going to find the derivative with respect to x and then solve for dy dx. So this is saying I'm about to take the derivative with respect to x. There'll be some dy dx's in there. Got to solve for it. So our first term, the derivative of x squared with respect to x is 2x minus, we have a product here, x times y. So off to the side, I'm going to do the product rule for x times y, and it's minus x times y. So we'll have our answer in parentheses there. So we have u equals x, u prime would just be 1. We'll have v is y, and then v prime is dy dx. So u times v prime is x dy dx plus vu prime, which is just y. Great. Then we have plus the derivative with respect to x of y squared. So that's going to be plus 2y times the derivative of y, dy dx, equals the derivative of 7 with respect to anything is just 0. So the derivative of 7 with respect to x is just 0. Now, students will normally get this part because this is kind of like the harder part, and you're very on the ball with that. But then they'll just write 7 here because it's so easy for us to forget that constant rule. So be careful, that needs to be a 0. All right, going into the next line, what I'm going to do is to distribute this minus sign through. Okay, distributing the minus sign will give us 2x minus x dy dx minus y plus 2y dy dx equals 0. From here, we need to get all of our terms with dy dx in it on the left. They already are, but move all the terms that don't have dy dx in it over to the right. So we're going to subtract 2x and add y to both sides. So over here on the left, we'll have, I'm going to write it actually this first and then this. So we have like the positive term first. So we'll have 2y dy dy dx, then the minus x dy dx term. Either way you write it's fine. I just like having the positive term first, so I'm going to do the same thing on this side and write it like that instead. Okay, then our next thing is to factor out the dy dx so we can solve for it. So what we have left in each term is 2y minus x. Then we're going to divide both sides by that 2y minus x to get dy dx by itself. And there we have it. We have our derivative, dy dx, the equation for it. So y minus 2x over 2y minus x. Kind of an interesting one. Then what we need to do is evaluate that derivative at the coordinate point -1, 2. So we are going to solve, well, I guess sort of solve. We're going to see what we get when we plug in -1, 2. When we plug in -1 for x and 2 for y, we'll have 2 minus 2 times -1 over 2 times 2 minus -1. That's a plus. So we have 2 plus 2 in our numerator, and we have 4 plus 1. So our slope is 4/5. So this is our derivative or our slope. We have our point, which was given, and now we can simply use point-slope form to find the equation of the tangent line. So using point-slope form, we'll have y minus 2 equals 4/5 x plus 1. And since this one's not too bad, I'm just going to actually solve it and make it look like in slope-intercept form. You do not have to. If you wanted to just write it like this to solve for y, that's totally fine. I'm just going to go the extra step real quick. So we'll have 4/5 x plus 4/5, and then that 2 is 10/5. So this will combine to be y equals 4/5 x plus 14/5. Let's take a look at this on Desmos and make sure it looks good. So this is really cool. Desmos allows us to plug in both x and y so we can have implicitly defined functions. So there we can see we have our ellipse. Next I'm going to, actually let's take a look at the coordinate point -1, 2. It's right here. So I want to plug in our equation of the tangent line. We can see that if you drew a tangent line here and you sort of follow this, it would definitely have a positive slope. So hopefully it works out. Let's see. Oh my gosh, it's so cool. It's so exciting when stuff works out. So we can see that it definitely hits at the coordinate point -1, 2. Here it is. And that is our tangent line to our ellipse. Awesome. Implicit differentiation is something I personally really enjoy. I don't know what it is about it. It's just super satisfying to solve for dy dx. So I hope you enjoy it too. It's a ton of algebra. It's not too difficult calculus-wise, and we use it a lot with things that are implicitly defined, such as ellipses, hyperbolas, and circles.